So if you see the previous recorded lectures, you can see the electromagnetic wave already have started. And today we'll see a typical type of, because previous class already we have started with the different Coulomb's law. What are the different applications using the Coulomb's law? That this portion we have seen, or rather we have started initially. But today's class, what we will do, we will see some basic Maxwell's equation, because Maxwell's equations, without the Maxwell's equations, we cannot proceed to the electromagnetic theorem. So the Maxwell's equation are the unavoidable part of the electromagnetic theory. So initially, we have to see certain amount of equations and what are the applications of the different types of equations that we will see. So if you remember in the, or rather if you see the classes of my recorded lecture, you will find the previous class, we have just completed the discussion regarding the Maxwell equation. So in this case, in this Maxwell equation, the different forms of equation we have studied. Now today we will start with the Coulomb's law. So this law, this is the developed in the year, if you see the 1785, that is long time ago. Expresses the force, yes, expresses the force between the two charges. So Q1 and Q2, suppose two different charges are there. In these charges, what will be the attraction between these two charges? That will be discussed under this Coulomb's law. So if these charges are positive, the force is repulsive in nature. So if you see the formula that is written in the equation number 1.3.1, if you see the structure of this particular equation, you will find that F1 to 2. So that is equals to Q1, Q2 divided by the 4 pi epsilon r square R12 cap. So this is the 1 to 2. That means the 1 is the initial charge, Q is the another point charge. So what will be the attraction? What will be the force between these two charges? That we can express using this Coulomb's law. So Q1 and Q2, that will be different charges divided by the 4 pi epsilon r square. R is the distance between the charges. R12 cap. This is the unit vector. And if you see the cap sign, so that is denoting the sign. So this is the figure. So if you see Q1, Q2, the two charges are there. With the two charges, one notation we are mentioning here. So this figure, the force between the two charges, Q1 and the Q2, the force is repulsive if the two charges have the same sign. Obviously, if we think about the polarity of the charges, the nature of this particular content will be changed. So they have written the R12, because this is the known thing. You have studied this thing in your physics classes also. So R12 cap, that is equals to R2 minus R1 divided by the mod of R2 minus R1. And what is this R? R is the distance between these two parameters. That means the R2 and the R1. Modulus sign. What we have, why we have basically taken the modulus sign? Because irrespective of the sign, positive and the negative, we can calculate the value of the R. So since the unit vector means this R12 cap sign will be a unit vector we have considered. The force between the two charges can also be rewritten as F12 equals to Q1 Q2 multiplied by the R2 minus R1 divided by the 4 pi epsilon R2 minus R1 whole cube. So R1, R2 are the position vectors. So this is the equation number 1.3.3. Next, electric field statistics. If we find out the electric field statistics, different types of statistics we are getting or we have to follow. So in this case also, the electric field capital E is defined as the force per unit charge. So what is the definition of the electric field? Because you know when you are transmitting any kind of signal, there is the existence of the electric field. Without the electric field, we cannot conclude, we cannot pass to anything. So when we are talking about the electric field statistics, that means what is the value of the or the net amount of the electric field, then we have to see this thing. That is the equation number 1.3.4. That is, again, we are calculating the force. And in this case, Q delta Q. Delta is basically the rate of change of, or rather the small change of charge content we can refer. So the electric field capital E is defined as the force per unit charge. For two charges, if there are two charges, one of charge Q and the other of this incremental charge, I have just mentioned a small amount of change. In this case, they are talking about the incremental charge amount delta of Q. The force between the two charges, according to Coulomb's law, we can express the thing, equation number 1.3.1, that may be written as like this: F equals to this Q into delta Q divided by the 4 pi epsilon r square r cap. This is the equation number 1.3.4. But r cap is a unit vector pointing from charge Q to incremental charge delta Q. Then the force per unit charge, that can be written as, if you want to calculate the unit charge, and if you follow the equation number 1.3.5, so we are getting the expression like this: capital E equals to F by delta Q volt per meter. So that is the net content we are achieving. So this is the equation number 1.3.5. So that this electric field capital E from a point charge Q at the origin is here. That may be written as the slightly modified version. So the equation number 1.3.6, that is basically consequence of the equation number 1.3.5, and we may write down the equation like this: capital E equals to Q by 4 pi epsilon R square into R cap. So many fundamental equations. Many of the equations already you have studied in your physics class. So that is a repetition kind of thing. Therefore, in general, the electric field E of R, certain distance if you want to measure the electric field from a point charge Q at R dash, is given by E of R. What will the expression? E of R equals to Q into R minus R dash divided by the 4 pi epsilon mod of R minus R dash Q. That is the equation number 1.2.7. So if you see, we are finding out step by step. Previous case we have not considered a certain point. In this case we have considered a certain point. That is E of a certain point is R. So E of R equals Q into R minus R dash divided by the 4 pi epsilon mod of R minus R dash Q. That is the equation number 1.2.7. And what is this R cap? R cap is this one. And if you one figure they have given, that is the figure this emanating the E field, that was the electric field from an electric point charge as depicted by the figure. So these 2 points they have considered, and they have drawn this particular figure. See the different types of arrow direction we have to follow. After this, we have to see the Gauss law, that is the statics. Again, we will consider this particular article, the statics function. So this law is also known as the Coulomb's law, as they are closely related to each other. We know there is a certain relation between the Coulomb's law and the Gauss law, and Gauss law and Coulomb's law we can easily correlate each other. Apparently, this simple law was first expressed by Joseph Louis Lagrange equations. So Lagrange equations, the famous mathematics, famous fields in respect to the electrical and the electronics engineering, the fundamental equations was developed like this. So this Joseph Lawrence Lagrange and later re-expressed by the Gauss in 1813. So this law can be expressed as this notation. This is a popular notation you have studied in your mathematics, that is called the surface integral d dot ds. So what is the notation? So d dot ds, that is equals to Q.
Hello, sir.
Hello, Kunjan.
Yes, sir.
So internet connection is very poor, Kunjan, for the system that is breaking. So if you see the formula, that is the express that can be expressed as Gauss law. So this is the notation for the surface integral. So surface integrals of d dot ds, that is equals to Q. This is equation number 1.3.11. This d is the electric flux density, coulomb per meter square. We know the value of the d equals to epsilon into E. And ds, that is the decremental value. If you follow the figure, you will see the notation ds we are following. So this capital D is the electric flux density, that is the unit to coulomb per meters, and capital D equals to epsilon E. ds an incremental surface at the point on S given by the D of S n cap. N cap is the normalized direction where they have mentioned the n cap is the unit normal, that is the unit normal pointing outward away from the surface. So in this particular notation we are basically following here. So the Q, obviously Q is the total amount of charge enclosed by the surface. So this is a different point. This is a different terminology that we have mentioned. Q is the initial point. D of omega we are measuring. D of S is a certain distance. So what are the different components we are getting that we want to express here? So the left-hand side of the equation 1.3.11, 1.3.11 means this is the surface integral of D dot ds. So if you see the left-hand side of this particular equation represents the surface integral over a closed surface. Already I have mentioned that is a surface integral, and that is basically under the closed surface contour. So the left hand side of this particular equation Kunjan, after completion of this Gauss law, I will terminate the class for today due to
Yes,
bad
sir.
network. Next week we can basically continue. I will basically continue the discussion
Okay, sir.
and we'll make up this particular class because today the internet connection is pathetic.
Okay, sir.
So in college, basically no net is there. I am using my mobile net and
Yes, sir. Okay,
I've
sir.
seen the output already, the disconnection.
Yes, sir.
Continuously we are facing the problem. Okay. So we have to complete this.
You're lagging, sir. You're lagging.
Are you
You're lagging, sir. Now it's fine, sir.
now we are getting now?
Yes, sir. Yes, sir.
Okay. So we are discussing about the equation number 1.3.11. If you see the shape of the equation, that is surface integral of d dot ds, that is the q. So d is the electric flux density, unit is coulomb per meter square. We know the expression capital D equals to epsilon E. ds is an incremental surface at the point on S given by the ds n cap, that is the direction point of view, where n cap is the unit normal point outward away from the surface. Q, what is Q? Q is the total amount of charge. So if you write down the expression like this way, so the left-hand side of the equation represents the surface integral over a closed surface S. To understand it, one can break the surface into a sum of increments. Just now I have mentioned, you can break the surface into different portion with a local unit normal Ni associated with it. So tail of Si is the notation we are using. For this reason, we have mentioned that is the n cap Ni. Ni cap. So associated with it, the surface integral. We can write down this thing. The surface integral can then be approximated by a summation surface integral of d dot ds. That is nearly equals to summation of I, because already we have split the thing into certain section. So summation of I di dot ni cap delta delta si. So this is equals to summation of I di dot delta si. So that will depend upon how many summation how many sections we have considered, because I will denote the number of intervals or the number of rotations we are using here. Number of sections we have basically mentioned the different surface integral closed surface, how many sum of the incremental surface, how many sections we have considered here, that will be denoted by the I. So equation 1.3.12, basically the closed surface integral of d dot ds, that is linear equals to summation of I di dot delta of si, where one has defined that delta of si equals to ni cap delta si. So in the limit where delta si becomes infinitesimal small, very negligible amount of delta si we are getting, the summation becomes a surface integral. So that will become the surface integral. Okay, let me check that the connection is there or not. No, till now we have not received the college internet. Okay, Kunjan, so I have to stop today's class because
Okay, sir.
internet connection. So next week, obviously, we'll continue the class and we'll basically make up this particular class
Yes, sir.
with next week, because the second half we have no classes now next week except this one.
I think so.
Yes, I think you have not other classes, so we can easily continue the session.
Okay, sir.
Next week. Okay. So thank you very much. Next week
Thank
we
you,
will
sir.
meet again, and before that, check your ERP. I will circulate this materials in your ERP. Okay.
Okay, sir.
Okay. Thank you.
Okay, thank you, sir.